part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss magnetic materials. Up until this point, we've been looking at the magnetic field due to given current distributions. So we calculate the magnetic field due to a long straight wire, we calculate the magnetic field due to a current loop, and so forth. Now we're going to look at the magnetic field due to matter itself. So in other words, those problems that we were looking at before involve the transport of charge. Now if you consider a permanent magnet, there's no transport of charge involved there. So in order to handle those kinds of problems, we're going to need to look on the atomic scale. Remember, magnetic fields arise due to the motion of charge. So if you look down at a piece of matter, magnetic material, on an atomic scale, what you'll see is you'll have nuclei, and they're being orbited by electrons, and then you also have electron spin as well. Viewed microscopically, those electrons give rise to tiny current loops, and those tiny current loops can be considered to be dipoles. Now, as a reminder, we calculate the magnetic vector potential due to a dipole, and write it on the board. So in other words, magnetic vector potential due to a dipole is equal to the permeability of free space over 4 pi times the cross product of the magnetic dipole moment and the separation vector over the magnitude of the separation vector cubed. And the magnetic dipole moment was defined as current times the area of the loop. Now I want to consider, since I'm considering matter to be composed of a bunch of dipoles, I'm going to define a new quantity called the magnetization. And that's equal to the magnetic dipole moment per unit volume. And the way you'd write that expression mathematically would be the limit of some volume as it goes to 0. Of sum of a bunch of dipoles within that volume. So basically the whole idea here is you want to take a volume that's small from this macroscopic standpoint, but it's large enough to contain very many dipoles, and they're not necessarily pointing the same way. In the absence of an applied magnetic field, for many materials, they're just going to be pointing in random directions. However, some materials do retain magnetization in the absence of an applied magnetic field. But broadly speaking, there are 3 classes of magnetism. We have diamagnetism, paramagnetism, and ferromagnetism. Diamagnetism means that the dipoles tend to orient themselves such that they reduce the total magnetic field. So in other words, they point in a direction opposite of the applied magnetic field. In paramagnetism, the dipoles align themselves with the magnetic field, and ferromagnetism means that the material retains magnetization even in the absence of an applied magnetic field. So a lot of times students get the sense that there's not really a lot of substance. You're not really fleshing these topics out too well in undergraduate electromagnetism. And there's a good reason for it. You really do need to go to quantum mechanics to explain these properly. So for now, what I'll do is I'll just leave these definitions, or rather let you keep these definitions in mind. Diamagnetism, the magnetization is in a direction opposite from the applied magnetic field. Paramagnetism, magnetization is in the same direction as a magnetic field. And ferromagnetism means that the magnetization persists even in the absence of an applied magnetic field. I will defer a more in-depth discussion of what each of these means for a later lecture. As far as if you really want to delve into the reasons why our materials, why do they exhibit this kind of behavior, well, you really need to be in a solid-state physics class. So again, if you feel like, well, we're not really fleshing these out as well as you'd like, the reason is it's really quantum in nature. So that being said, let's assume now that we just have some kind of material that has a magnetization. And we'll forget about, for the time being, why that magnetization arises. Just want to figure out what the magnetic field is in terms of that. So let's consider uniform magnetization first. That, give myself a little bit more room. So let's take a slab of material. And we'll assume that, or rather I should say, since we're assuming that the magnetization is uniform, each of these dipoles has the same magnetic dipole moment. If you look on the inside, or consider the interior of this slab of matter, what you'll notice is that the little currents tend to cancel each other out. Because right here, this current is going that way and going in this direction, but yet from this adjacent current loop, current's going in the opposite direction, so they cancel out. But that's not the case around the edges of the slab. So in other words, here everything's going in this direction, there's nothing to cancel out. So even though there is no charge transport, the effect, or the circulating current, gives rise to an effective current about the whole slab itself. So in other words, effective current is going in this direction. Magnetization is pointing upwards, and out from the slab is in the normal direction. Since we are assuming that each of these little dipoles is the same, I can write my magnetic dipole moment as magnetization times the volume, and that'll be the volume of one of these little current loops, so that's of area A, and we'll assume this slab has thickness D, so it's mad. But it is also true that your dipole moment is equal to the current times the area. So setting these two sides equal to each other, the current is equal to the magnetization times the thickness. And this is current per unit length, and that is going to give rise to a surface current density. And it has direction perpendicular to the magnetization and to the normal slab. Okay. Now let's consider what happens when you have non-uniform magnetization. We consider two adjacent volume elements here. We'll assume that they're both of width delta y. And the amount of current, we'll assume the magnetization is different, so that's indicated by the slightly larger current symbol here. And this is magnetization at y position, and this is at y plus d1. My goal here is to figure out what is the net upward current. So how do I do that? Well, I'm going to write the magnetization in terms of the current, or you can think of it vice versa. So in other words, for the left-hand side, we have left-hand side times delta y, delta z. That's equal to the x component of the magnetization times the volume of this cell here. Now on the right-hand side, I'm going to make an expansion of this. This is just equal to mx plus almost ran out of space here. Plus partial derivative of mx with respect to y times delta y times the volume of the cell. There are also higher order terms, but we'll assume that those are negligible. To figure out the net upward current, well, from this side it's going up, from this side it's going down, so I'm going to take the difference between these two. Difference between these two, I'll see that I left minus I right. Is equal to minus the partial derivative of mx with respect to y times delta x delta y. So basically it's this area right here. Okay, that's not the only current I have to consider. Let me sketch out, better yet, erase this. Actually, let me reverse this. Because x is positive out of the board, so we have my x plus dx, and here we have my of x. I'm going to follow the same procedure as before. I'm going to figure out what's the net current upwards. So in the front, it's times delta x, delta z is equal to my plus partial derivative of my with respect to x, delta x times delta x, delta y, and delta z. The contribution to the current from the back cell is equal to my times the volume of that cell, which is delta x, delta y, and delta z. The net current in this case is I front minus I back the net of both of these adjacent cells, I front minus I back, is equal to the partial derivative of the y component of the magnetization vector with respect to x times delta x, delta y. So the net current altogether is the sum of both of these. So this is a net current going upwards. Therefore, I up is equal to partial derivative of the y component of the magnetization with respect to x minus the partial derivative of the x component of the magnetization vector with respect to y, delta x, delta y. Divide both sides through by delta x, delta y. So in other words, this area up here, that's going to give me a volume current density. So that, in fact, I'll erase that. Is going to be the z component of the bound volume current density. I can extend the argument to all three directions, and if you notice the right-hand side, this is just the z component of the curl of n. So therefore, generally speaking, the volume current density, or bound volume current density, is equal to the curl of the magnetization vector. And I'll start from before. Bound surface current density is equal to the cross product of the magnetization vector and the normal to the surface of the material. Okay, so this was a qualitative discussion of how to define these two quantities. I'm going to go for a more rigorous discussion of that. Erase all of this. Now let's begin with this expression for the magnetic vector potential due to a dipole. So, dipole moment per unit volume, and really I should have the summation over here. But anyway, if I can replace this by an integral it's useful to rewrite this in a little bit different form. And recall that if I take the gradient of separation vector with respect to prime coordinates, that's equal to the separation vector over the magnitude of the separation vector cubed. And notice if I'd taken it with respect to unprimed coordinates, there would be a minus sign out in front here, okay? But anyway, this is mu naught over 4 pi. And I'm going to write the dependence on prime coordinates so that it makes that explicit. And this is the cross product of gradient of 1 over r minus r prime and integrated over the volume of the magnetic material. I'm going to make use of another vector operator identity, and that is to say, if you take the curl of the product of a scalar and a vector, that is equal to the scalar times the curl of the vector minus the vector crossed into the gradient of the scalar. Now if I can identify 1 over r minus r prime as little f and magnetization as capital M, I will get 2 terms here. And the first one will be curl again with respect to prime coordinates. The magnetization vector over the magnitude of the separation vector plus mu naught over 4 pi volume integral of the curl of the magnetization vector over magnitude of the separation vector. And making use of an integral theorem, I can convert this volume integral to a surface integral. So that'll become plus mu naught over 4 pi And lo and behold, if you look at the numerators here, on the first term, that is just the bound surface current density. And I'll leave off all the primes and arguments here. And in the second term, the numerator in the integrand is the curl of of the magnetization vector. So the whole point of this is that even though with magnetic materials there's no transport of charge involved, there's an effective current due to all those tiny little current loops. And that gives rise to a bound surface current density, bound indicating that there's no transport, and the bound volume current density, which is equal to curl of the magnetization. Okay, so let's do an example here. Consider a very long cylinder. And let's suppose that the magnetization is defined as some constant k times the radius s and oriented in a circumferential direction. And I want to figure out what's the magnetic field everywhere, inside and out. How do I do that? Well, first order of business is I'm going to calculate what the bound current densities are. So in the first case, let's look at the bound surface current density. So this is Ks V cross S. Normal to the surface of the cylinder is in a radial direction. So that is evaluated at, or is on the radius surface of the cylinder. So that's equal to minus Kr in the z direction. Now what about the volume current density? In this case, magnetization is only in one direction. It's only in the circumferential direction, and there's only dependence on the radial component. So therefore, the curl in this case only has one surviving term. And that is 1 over s partial derivative with respect to s of s times the n component of phi. And that's in the z direction. Equal to 2kz. So how do I figure out what the magnetic field is? If I try to use those expressions that we just derived, magnetic vector potential, and then after you go through all the mechanics of that, if you will, and figure out what the curl of that's really an onerous task. It's much better if we realize, well, this problem has symmetry to it. So if you know what the current distribution is and it presents the proper symmetry, you can make use of Ampere's law. Ampere's law tells you that if you take the line integral of the magnetic field around a closed path, that is equal to the permeability of free space times the total amount of current enclosed by that loop. So in other words, total amount of current that passes through or flows through that loop. Now, it doesn't matter whether you're talking about bound current or free current, the total current. So what I can do is I can construct 2 Amperian loops, one inside and outside, because that's what I want to figure out. Both Amperian loops are circular and they're coaxial with the very long cylinder. So therefore, on the left-hand side, you'll wind up with 2 pi s times b. And let's tackle the interior problem first. So in other words, s less than r. Over on the right-hand side, that is equal to the surface integral of the volume current density dotted into the normal. Currents inside is flowing this way, and the normal to this little area enclosed by the loop is in the z direction. So therefore, we'll wind up with mu naught times the surface integral of 2k s ds d phi. That's the area element. Now doing math, you will wind up with u naught times 2k times 2 pi times s squared over 2. And therefore, magnetic field has magnitude k u naught ks, and that too will be in a circumferential direction. So look, lo and behold, your magnetic field has a very simple form in terms of magnetization. It's just equal to mu naught m. Okay? What about outside? So we have an Amperian loop that's circular and coaxial with the long cylinder. And also we know that B is in a circumferential direction because of the symmetry of the problem. So we've got the volume current density that we've got to take account of. And then we also have to take account of the surface current density. First case, we'll wind up with mu naught kr squared. Put all the 2's in there so don't lose track of anything. So integral over the s component, that'll be r squared over 2, and factor of 2 from 2k, and then also the 2 pi from integrating in around phi. Second term will wind up with minus mu naught k times 2 pi r squared. That cancels for that. And you see that these two terms have equal and opposite signs. So what that means is the outside, the magnetic field vanishes. Does that always happen? Obviously not. You do, after all, have permanent magnets, and there is a magnetic field outside, but it's just because of the symmetry of the problem. It's just I chose magnetization to be in a circumferential direction, and that's what enabled me to make use of Ampere's law, because the current densities have a proper symmetry. And it's just in this case, magnetic field is just equal to mu naught m. Inside, outside, it vanishes. That is not always the case, so it's only because of the symmetry of the problem. I'll leave this up here for a minute, and then we'll move on. Okay. So curl of the magnetic field is equal to mu naught times the volume current density. That's Ampere's law in differential form. I'm going to divide both sides through by mu naught. So we have mu naught curl of B is equal to J. Now, in this case, we're talking about all the current, not just free current or current associated with the transport charge, or conventional current if you prefer. call that F. We also have the bound current, okay? But we just derived an expression that the bound current is equal to the curl of the magnetization. So I'm going to pull this term over to the left-hand side. And wind up with curl of the magnetic field divided by mu naught minus the magnetization is equal to the free volume current density, or the conventional current, or if you prefer, the current that involves charge transport. I'm going to introduce a new vector quantity, and I'll call this H. So this is the auxiliary field, or H field, and that is just curl H is equal to the free volume current density. Call back to electrostatics. We introduced the electric displacement because in certain cases it's a lot more convenient to work with D, where you actually make the free charges explicit and separate things out nicely. It sort of made problem solving a little bit easier in some cases. We're doing the same thing here. We're separating out the free current density from the bound current density, and we wind up with curl H. So Ampere's law for magnetic materials, if you will, can be written as curl H is equal to, or rather, line integral of H around a closed path is equal to the total amount of free enclosed current. And notice here we're not saying, well, H only depends on the free current. It doesn't. It does depend on the bound current. But if you have systems that present a certain degree of symmetry, this makes life really easy. And I'll show you this one example. Let's suppose that you have very long cylinder that has magnetization MZ. And I want to figure out what's the magnetic field due to that very long cylinder. So Ampere's law for magnetic materials tells me that the line integral of H around a closed path is equal to the total amount of free enclosed current. There is no free enclosed current. So H equals 0 everywhere. What about inside? What about B? Well, you know your auxiliary field is equal to B over mu naught minus M. So if H is 0 everywhere, that means inside cylinder. B is equal to mu naught times N. Outside B is equal to 0. Notice this only happens because of the symmetry of the problem. Okay? Let's take one more example. suppose that we've got a very long wire. And let's suppose it's made of copper. And I want to determine what's the magnetic field. And we'll assume that the current is uniformly distributed. But notice I am not saying anything about the magnetization, so magnetization we'll assume is unknown at this stage. And so, how do we figure out the magnetic field? Well, if the current's flowing in the z direction and we have radius r, again, we're going to take Amperian loops that are circular and coaxial with the cylinder. So therefore, inside we have 2 pi s, that's the distance around the Amperian loop, times h, and it's symmetric, so we know that the magnetic field, or the auxiliary field I should say, has the same value at all points equidistant from the axis, provided you're talking about all those points right along here, okay? So that's 2 pi s h on the right-hand side. The total amount of enclosed charge is equal to volume current density, free volume current density dot n dA. So that is going to be equal to the current over pi r squared, because it's uniform, and then the area of the Amperian loop, so it'll be pi s squared. So therefore, h inside is equal to s over 2r squared is over 2r squared, and that'll be in the circumferential direction. And can't leave off that pi. Okay? What about outside? Well, we've got a total amount of current flowing through, so basically it's going to give you I over pi r squared times pi r squared. And therefore h is equal to I over 2 pi s in a circumferential direction. Okay? Now, I don't know what the magnetization is. I'm just told what the current is. So therefore, I can only say outside, I know B is equal to mu naught H or mu naught I over 2 pi s. Inside, I know what the magnetization is. However, I will say that if you have copper, the magnetization is going to be very, very small due to the fields. So therefore, for all intents and purposes, this magnetic field will just be mu naught IS over 2 pi r squared with a very small correction to that. Okay? So I'll leave that up on the board for another minute.